Hi folks. This week we're going to do something a little bit different. Usually we have some high entertainment value trailer for next week's material, but I thought it was worth looking at why we actually care about inflection points, because it's pretty topical to what's going on right now in the world. So I want you to think for a second about extreme values and points of inflection on a smooth curve. We've got this curve in front of us, which has a min right here, and a max right here, and a min right here. And if I wanted its points of inflection, looks like there might be one right here, and maybe around here, and here again. Now when we look at functions in math, often we can see a good chunk of them to the left and right of wherever we're interested in. But imagine that you only saw a little bit of this. Let's zoom in. Let's say that this represents something that's actually important to us, and we notice that it's gone down and it's hit a minimum, and then it's rising again. And right here, it probably looks like it's going to rise forever. And now I keep looking over. Yeah, it's rising pretty quick. It's rising, and suddenly I notice it starts rising at a slower rate right over here. Its concavity has changed. And what does that make us think? It makes us think that there might be a maximum that's coming down the pipe. And if we keep going, oh my gosh, that maximum does happen. Let's look at it further. It's decreasing. And again, if I just saw this much of the decreasing curve, I might think, oh, it's going to decrease forever. But as soon as I see that inflection point, and things start to change, and I think, oh, maybe a minimum is coming. It's almost as if these inflection points serve as early detection systems for a max or a min. Now, it's not guaranteed to happen, but it's a way that we can start to be a little suspicious that a max or min might be coming up. So if a curve is increasing, a point of inflection is a hint that a max or a plateau may be coming. If a curve is decreasing, a point of inflection is a hint that a min or a plateau may be coming. To give this some context, here are three curves that might represent the tons of carbon dioxide in the atmosphere over time. And if we thought of them in terms of most comforting to least comforting, probably this one in the middle is the most comforting. Okay, now out of the other two, they're both increasing, and they don't look like they're stopping increasing, but the one on the far right has a point of inflection. At the very least, the rate at which it's increasing is slowing down. And that gives us hope that either this might happen, where it sort of plateaus off, or, even better, maybe it will turn around and look like that middle graph. Whereas the one on the left is probably the least comforting one, because it's just going up and up faster and faster. Points of inflection are particularly important in mathematical modeling. Chemical reactions, species populations, and disease spread are often modeled by a logistic curve, sometimes called a carrying capacity curve or a sigmoid. And that kind of curve exhibits a lower bound, horizontal asymptote, so basically as low as you can go, and an upper bound asymptote, as high as you can go, or approach. And the behavior of the curve is such that in the beginning it grows quite slowly. If I trace this curve, it really doesn't look like it's growing much at all in the very beginning. And then it starts to grow really quickly. Next, its rate of growth starts to cool off a little bit, and finally, in the end, there's almost no growth. The point where the rate of growth changes from being increasing to decreasing is that point of inflection right in the middle. And here's an equation for one. 1 over 1 plus e to the negative x. And that can be played with. Let's again just look at the curve, though, bit by bit. If you're living through a phenomenon that has this sort of property, then really you only see bits of it at a time. So it increases, looks like it's increasing exponentially, and then its concavity starts to change and you think, oh, maybe it will turn around or at least level off. So that most important point on the curve is the point of inflection. So even if we saw the curve only up until x equals 1, we'd start to have some hope that the curve might plateau in the not too distant future. And here's a look at that curve right until x is 1. Starts to slow down. Graphically, we could see that point of inflection at x equals 0, but we can also use calculus to find it. So here's the original function. I rewrite it as an exponential, and then I start to do some chain rule stuff. I start to do some quotient rule stuff. Eventually I get my second derivative. I simplify it. And right down here is a simplified version of the second derivative, which has a critical value of 0. And then I test around 0. I find out the concavity changes. Point of inflection at 0 and 0.5. Just like any other function. Maybe a little bit rougher than many of the ones that we've dealt with so far, but the technique is still the same. Here's a graph of a real-life phenomenon. We're looking at the number of COVID-19 cases in South Korea, and this is up until April 27th, and this is from worldometers.com. You can see the shape of that curve is very much a sigmoid or a logistic curve, just like we saw before. Does it look perfectly like the idealized version? Maybe not, but it definitely has that property where it is increasing quickly and then less quickly and sort of tapering off. So if you're living this curve, this is not great. You see that it's concave up and increasing, concave up and increasing. It's not until we start to see a point of inflection. And it takes a little bit after the actual inflection to be sure that maybe you've seen one. I think it looks kind of like around here, maybe. And maybe that was a little bit too far to the right. But it's at that point that you start to have a little hope that things are going to improve. And then the more the concavity is negative, the better the outcome looks like it's going to be. When we see the whole curve like this, we have the benefit of a little bit of hindsight, but as you're going through the phenomenon, it is that point of inflection that makes you think maybe things are about to improve a little bit. So seeing a point of inflection gives us hope for overall improvement. It also makes it easier to develop models for the future spread of the disease. Once you know the inflection point on a logistic curve, which here looked like it was around early March and around 6,000 cases, then you know the midpoint of the curve, and you can stretch and shift the curve to fit your data. We already know a lot about transforming functions. We know that you can have a vertical stretch factor, a horizontal stretch factor, you can have shifts and lifts. So if I took that basic logistic function and started to mess with it, it could have these properties. So if we have some fictitious situation where we have an inflection point at 8,000 cases, 53 days after the 100th case in some country, and often these figures are counted after days after the 100th case, you might be able to generate a model with that information. You'd want to put your midpoint at 53, 8,000, which means a vertical stretch factor, which means a shift of 53. And then I played around with B, or I could have done it analytically, to make sure that when X is 0, I've got 100 cases here. And this is how I might think that the spread is going to play out through some mathematical modeling. And the most important point on that curve is that point of inflection, where it changes from the rate getting faster and faster to slower and slower. Now, the internet is full of so-called experts, so let us not kid ourselves and think that now we know exactly how the spread of a disease is going to look in a given situation. These are just models, and we are not experts in generating the models. A country may experience several points of inflection, and you can go to Worldometers and check different situations that have come up. or it may not look like a logistic curve at all. All models are based on assumptions, but generally a good or reasonable model is better than none at all. But just to keep our foolish pride in check, let's list some of the assumptions we've made in generating our curve. Here are a few that I can think of. I'm assuming that it's going to continue on trend, that I had a reasonable curve choice in the first place, that similar social policies are going to remain in place and that there's not going to be some big difference in those. And another assumption that I'm making is that a vaccine is not going to be suddenly developed. All of those things are going to impact the model, but having a model might be useful. It is not a crystal ball, though. So this might immediately make you think of, is this what flattening the curve is all about? And the curve we've been looking at is the total number of cases. If you were to flatten it, that would mean bringing down the upper bound, which would be fantastic. Typically, when people talk about flattening the curve, though, they mean the number of new cases per day, or the number of active cases, rather than the total number. The total number is never going to go down. It's like the odometer on your car, only counts up. So here's the data for South Korea again, but this time it's represented as new cases in each day. And you can imagine if you flatten that curve, then you might bring down that max. This would be a pretty ideal version of flattening the curve, where the max still occurs at the same place, but it is just much lower. Another type of curve flattening that could occur involves having the max happen later but not be as high. And both of those are about making sure that the healthcare system is not overwhelmed by too many cases at one time. One thing you might notice about this daily new cases graph is where its max is. It's kind of around here-ish. We've got a max in late February, early March. If you take a look at the total cases graph in early March, you're seeing that point of inflection. So the max on the daily cases, or the new cases, corresponds to the point of inflection on the total cases. Those two things are related to each other. Now we're going to bring it back to calculus for a minute. Let's take a look at that graph that we generated for our hypothetical situation. There it is. It's a logistic curve. If I graph its derivative, that's down there in blue. And it's going to have some meaning. The y in this means cases, or total cases, and the x is per day. So when we find the derivative, it'll have some meaning. Check out our point of inflection. If you look at the derivative curve, that point of inflection corresponds to the same place that the max is happening on the derivative. Let's think about these curves. In the first one, the logistic curve, you had y as number of cases. In its derivative, you would have dy by dx. And what is that measuring? That is measuring cases per day. Or you could think of that as new cases per day. So calculus is at play here. The total number of cases is related to the cases per day. The cases per day curve is the derivative of the total cases. The max on the cases per day curve corresponds to the point of inflection, which we care about very much on the total cases curve. And by flattening the curve, you are changing the max on the cases per day curve, and you are impacting the point of inflection on the total cases curve. We've gotten a bit of a flavor for what the mathematical modeling might look like, a bit of insight into how the derivative's working, but really we don't have a ton to work with at this point. The big idea we want to take away from this, though, is that points of inflection are important because they serve as early detection systems for major change. That change can either be a max value or a min value, or it can be a plateau. And that's important as you're living through a phenomenon. If you see this, that's not great, assuming that it's a phenomenon that is not ideal. Okay? But as soon as we go from this to that change in concavity, that's where we think, oh, maybe something will change. Maybe it will be a max, or in this case, or maybe it will be simply a plateau. Either of those things are better than boundless increase. It's also possible that they'll just lead to another point of inflection before anything too interesting happens. So it's important not to treat an incomplete model as some kind of fortune-telling device. For example, if I have a curve that's increasing like this, and then there's an inflection, it's possible there'll just be another inflection before I get a max or a min. But points of inflection should get our spidey senses tingling for the possibility of a change in the behavior of a curve. And that is one big reason that we care about them very much.